Hello everyone, welcome to the last lecture of week 5 of the course Power Network Analysis, in which we will start with a new module, the 5th main module, which is going to be on transmission line models and use of these models to understand the performance or behavior of these transmission lines under different operating conditions. Specifically in this first discussion of this module, we will start with the basics and understand at length what are the two-port networks and how can these two-port networks be used to develop the relevant line models that we are talking about. Till the last lecture, we had finished up with our discussion on evaluation of transmission line parameters, in which we saw that a typical transmission line attributes to some properties which are line resistance, line inductance and line capacitance. How these attributes or parameters come in, be it AC resistance, DC resistance, line inductance due to magnetic flux lines, line capacitance due to electric flux line interactions, and etc. etc. So all those were discussed in the last module. Line conductance specifically is difficult to model, and hence it was not detailed discussion was not done. We considered it to be a negligible quantity. Starting with this module, our aim would be to understand the steady state performance or characteristics of these three-phase transmission lines, which tend to have these non-negligible attributes, and we will try to develop certain mathematical analytical relationships between the terminal voltages at the ends of the line and the current through the line. We'll also understand how to replicate or evaluate the associated single phase line models, which would be very crucial for the upcoming modules which are going to be on power flow analysis, fault analysis, and lastly stability analysis. As I mentioned, these modules would be very useful in understanding the steady state performance as well as dynamic performance. Steady state performance mostly from the perspective of power flow analysis, whereas some aspects of dynamic performance would be useful in understanding the fault analysis and stability analysis modules for a given power network having these transmission lines. The certain models that we would develop or discuss, we won't talk about them specifically, but definitely certain models which are very useful for lightning analysis or lightning strike analysis and for fault analysis in DC networks. Those modules or those models could also be developed based on the models that we would discuss. So all those would be discussed as and when required. For the fault perspective, where I mentioned the dynamic performance would be useful, by fault analysis, I specifically mean it is only for AC networks and not for DC networks. And I'm sure all of us understand the difference between these AC networks and DC networks. AC networks are where there is a source frequency, 50 Hz or 60 Hz, whereas DC networks, they don't have a typical zero crossing, specifically from the perspective of voltage signals and current signals, because it's a DC network. So coming to transmission line models, what is shown over here in this figure is a typical three-phase 500 kilovolt double circuit transmission line. Why it is called as double circuit? Because one circuit is pertaining to each of these individual towers. Circuit number 1, this is circuit number 2, and in each of these circuits we can see, for each of the towers we can see there are 3 dedicated phases which can be easily clear marked, and along these 3 phases there are also double circuits present along each transmission tower. So if these 2 phases, let's say, correspond to phase A, these correspond to phase B, these correspond to phase C. So essentially it is a 4-wire circuit or a 4-wire circuit, each tower having two circuits. And each of these phases, if we see specifically over here, we can see few sets of conductors running in parallel. There are precisely 4 such conductors, 4 bundled conductors. And the impact of the role or the necessity of having bundled conductors, we have discussed at length in the previous module, and how does this bundling lead to the impact on transmission line inductance or capacitance, that aspect we have also seen. And The transmission lines, they don't have a physical contact with respect to the towers. There are strings of insulators, the small encircled ones which you see, and typically for a 500 kV transmission line, the number of insulators would be somewhere between 21 to 23, assuming each such insulator has a voltage handling capacity of around 21 to 22 kilovolt. And the reason why these transmission lines are not directly in contact with the transmission tower is because from the perspective of safety, number one, the personnel who is working on these transmission towers might get electrical shock if that line touches the transmission tower. And furthermore, the purpose of having these towers is to set up a transmission line which can carry power from generating stations to the load end stations. If in between a short circuit happens, then the normal flow of current, that path is interrupted, and if there is a physical contact, essentially current or power, it would all go to the ground through the transmission tower if tower and line comes into contact, and that's the reason why insulators are present. There are also extra steel conductors which is probably visible over here. These conductors are placed on top of the tower and they act as a good guard against lightning, providing shielding or protection to the transmission lines as well as tower. And the impact of this ground wire, it is already incorporated while considering or evaluating line capacitance. So given this typical transmission line towers and models, some of these towers could also act as transposition towers. Now let's see how can we develop some steady state model specifically from this model perspective for these transmission lines which are on overhead erected through the help of transmission towers. So what we understand or what we can conclude from the previous module discussion is that actual three-phase transmission lines, they all have distributed parameters, and that is the reason why our line resistance, line inductance or line capacitance, they were evaluated on per unit length basis, which means that if the line length is of 1 meter, then the effective, and these R, L and C are evaluated on a per meter basis, then the corresponding line with 1 meter length would have a net resistance of small r, net inductance of small l and net inductance of small c. L and C can also contribute to the corresponding reactance. So basically, actual transmission lines, they all have these distributed parameters in the sense that every section of the line length can have these individual or uniform R, L and C values. So if the line length is 1 meter, then the total resistance or reactance is R and X. If the line length is 1 kilometer, then the total resistance or reactance is 1000 R and 1000 X, assuming R and X are evaluated on a per meter basis. Now, given the transmission line, if the question comes that, okay, let me know where is that precise location or specific location where this 1000 R resistance or 1000 X reactance is present in the transmission line. It would be very difficult to exactly pinpoint out that specific location where 1000 R resistance is present and 1000 X reactance is present. Reason, the transmission line is having the same material property, same electrical property through any section that we take. So essentially, every smallest section of the transmission line will have these distributed properties, and hence it is not possible to pinpoint one specific location where the above resistance or reactances are present in a lumped fashion. So the question comes is it always essential? Because if that's how our transmission lines are designed, they are supposed to have distributed properties, and that's the reason why we have evaluated our reactances and resistances in the previous module on per unit length basis. Is it always essential to have three-phase lines modeled as circuits having distributed parameters? The answer is at times yes. The answer could also be at times no. Where the answer is no is because transmission lines, when they are modeled as lines with distributed parameters, the relevant equations that would come up, not in today's discussion, but hopefully in the upcoming 4th or 5th lecture in this particular module, we would understand and see that line models with distributed parameters will involve some non-algebraic equations. To be specific, these equations would be differential equations. If we talk about these equations in phasor domain, then yes, these would be differential phasor equations. If you have time domain signals or time domain representation, then the differential part would also come in from the perspective of time also. Now, handling or solving these differential equations obviously is not so straightforward in the context of power networks as compared to handling or solving algebraic equations. So that's where comes a attribute of having a trade-off. The trade-off is whether we should complexify our model to the extent possible so that we can get the best possible accurate result. The time involved in getting that accurate result might be higher, or the alternative could be, okay, let's not complexify our model so much, let's try to bring in certain assumptions, and even with those assumptions, the analysis that we would get after solving those relevant equations would still be close enough to the most accurate result. Benefit could be in terms of time. One can save time in terms of getting these accurate and non-accurate results. So that's where the trade-off aspect comes in. So the takeaway is not all lines need to be modeled as circuit with distributed parameters. The equations that would come up need not always be differential. We can simplify our model, assume these line resistance and reactance to be lumped at a specific line location rather than being distributedly present across any section of line. And given that trade-off of how we want to model our transmission line, the line could have lumped parameters also. Again, lumped parameter is not an actual representation. It is coming in from the perspective of the trade-off required between complexity of the model and the accuracy of the solution behind defining the transmission line performance. Also, we have understood in the previous module that transmission line operation, it is often balanced thanks to line transposition at the transposition tower. And since it is mostly balanced thanks to transposition, we could also have our per unit analysis or per phase analysis instead of analyzing the entire three-phase circuit. So our focus would be on understanding where we should use distributed parameters, where we should use lumped parameters, and using these distributed and lumped representation, how can we get the equivalent per phase model of the three-phase transmission line, because our transmission line are often balanced in nature in terms of operation. So in context of transmission line models, there are different types of models that can come up. These mostly depend on the physical line length, whether the line length is of few miles, few thousands of miles, and also the operating voltage, whether it is a distributed line, whether it is a subtransmission model line or a transmission level line. And by operating voltage, I would specifically mean the line-to-line RMS. So typically in the literature of power networks, there are three such typical categories or models of transmission lines. The first one is called as the short line model, which essentially is applicable or has enough accuracy with simpler complexity to understand the performance of lines operating less than 69 kilovolt line to line again, and line length not being more than 80 kilometers. The second line category model is medium line model, where the line length is typically between few hundreds of kilometers to few 300s of or 250 of kilometers, and operating voltage is between 69 kV to 400 kV. And the last line model is the long line model, where line length is very high and operating voltage is beyond 400 kV, operating at extra high voltage. Now, given this three typical line models, the terms that you often would see or specific are the term being short, the term being medium, and the term being long. It might appear that these terminologies of short, medium, long, they are coming in because we are associating these models with respect to the corresponding line lengths. There is a word of caution that one should have before understanding or having this understanding. The word of caution is, please don't associate short, medium, long with only the line length. The operating voltages are also important. So for example, if there is a line which is of, let's say, of 200 kilometers, and the operating voltage is at 765 kV, then if you look at the numbers or definitions of medium line model, the distance very well qualifies it to be called as a medium line model, but the operating voltage doesn't qualify it to be a medium line model. So operating voltage being more than 400 kV, this attributes indicates that it should be modeled as a long line, and that's how the accurate performance analysis can be done. So overall story, if a line length is of 200 kilometers and operating voltage is beyond 400 kV, it is preferred to model this line as a long line irrespective of what the line length is. Again, as power engineers, we do understand or consider the aspect of trade-off. If the line length is substantially small, let's say a few 50 kilometers or hundreds of kilometers, then unnecessarily modeling this particular line as a long line might result in taking more time. So, depending on the need of the performance which needs to be done, whether it's for steady state or whether it's for dynamic performance, the corresponding line could be modeled as a medium line or a short line. So, given this, understanding that short, medium, and long need not always refer to the line length. Each of these transmission line models, they differ in terms of whether distributed parameter is considered or lumped parameter is considered, whether what type of line parameters are considered. Usually you would think that, oh, all these line models would have resistance, inductance, and capacitance. No, it's not always true. And depending on these representations of distributed or lumped and which quantity or attribute is being modeled or considered, the governing equations could be pure algebraic equations or they could also be differential equations. And all these considered together results into what trade-off is necessary between the line complexity, the line model complexity, and the accuracy of the solution which is desired or defined to assess the precise performance. Bottom line story or end story is, no matter what the line length or operating voltage is, each of these transmission lines, they can have the same ACSR conductor. The type of material used for short line, medium line, long line, they need not be different. It is the same transmission line which has the same R, L, and C on a per unit basis. Depending on the line length, depending on the operating voltage, the corresponding model could be different, but the material is going to be material or type is going to be common in all these different line models. So before we go dig deep into what these line models are, we would very significantly make use of concept known as two-port networks. Now, two-port networks, what do they do? The two-port networks, they help in defining and establishing these analytical expressions, which could be again differential equations or could be algebraic equations in phasor domain, and they also help in figuring out the per phase equivalent of this three-phase transmission line. Because essentially when we talk about line model, their performance, we need to understand how the line losses are, how the line is behaving at different operating voltages, different voltage levels, different load voltages. So as the name suggests, a two-port network, it has two pairs of ports or terminals, both could be used, and one pair or one port or one pair of port is usually assigned the notion of input end or sending end, and the other pair of port could be called as the output end or the receiving end. Usually sending and receiving, they come from the perspective of that, okay, if a line parameter or line port is being called as a sending end, usually that end is having some sort or some form of a source, voltage source or generating source, and the receiving end is generally associated with the fact that there is some physical load which is drawing power from the source through this transmission line. That's the notion of sending and receiving end. So it's mostly from the perspective of how power is flowing, essentially, effective power. And different types of parameters have been defined to sort of explain or represent these two-port networks. We will, in our discussion, take up four typical such parameters useful for defining two-port networks. Before we go deep into what these parameters are, I just want to make it clear that what type of two-port network am I talking about. So I have this transmission line with some sending end on again on a per phase basis. I have this transmission line with whose line length is of few kilometers, operating voltage is again few kilometers. The second port that I have drawn here could refer to the equivalent neutral, or it could refer to the equivalent ground, from which the sending end voltage Vs and receiving end voltage Vr are being measured on a per phase basis. And this entire transmission line can be considered to be modeled through this black box, which we call as the two-port network. This black box could have different parameters, which we will see at length. And since this black box is having a dedicated sending end, which is having the subscripts of S on voltage Vs and Is being the sending end current. Similarly, the other part is being assigned as a notion of receiving end, essentially meaning there is some load present here. And that's the reason of why having a small r in IR and VR, IR being the receiving end current, VR being the receiving end per phase voltage. Now, different types of representations could be present in different textbooks, in different literature. In our discussions to come up or follow, we would simply assume IS to be always a input current to the two-port network, whereas IR would always be a output current for the two-port network. Certain references could also have IR being represented as also an input, and since this is the sending end, so corresponding the return current could be in the reverse directions. We are not going to have this terminology. So if you understand these aspects well, you can also apply them to reverse notation of receiving end current. The first common parameter that we would see would be called as the Z parameters, and usually if you recollect the variable or symbol Z, Z is often associated with line impedance in power network discussion or power network context. So Z parameters essentially are few impedance based parameters which are defining the property or attribute of this two-port network, with sending end and receiving end quantities being marked the way they are as we saw in the previous slide. So if these parameters are impedance based parameters, that means the corresponding equations which are likely to come up, they are relating some voltage with respect to some current multiplied by the corresponding impedance. That's how the impedance or basic Ohm's law definition is. V is equal to IR, so IR is also a form of impedance. If you're talking about Z parameters which are going to be impedances, so basically for an equation on the left hand side there should be a voltage expression equal to a current expression multiplied by the corresponding impedance. That's how impedance or ohms are defined. So in context of Z parameters, this expressions or equations would be parameters. Let's say we call them as Z11, Z12, Z21, Z22. These Z's would essentially indicate an equation which is of the form V is equal to Z into I, where Z are the Z parameters, V is voltage, the parameters are in ohms, and here I is in terms of currents. And we have four such parameters, Z parameters. How do we relate these Z parameters in terms of the equations that are going to come up? So for this two-port network, Z parameters are nothing but Vs. So we have two voltages, remember, one on the receiving end, one on the sending end. And if we are using Z parameters to represent these voltages and currents, so both these voltages should be present. So VR is over here. In terms of Z parameters, Vs is Z11 into Is minus Z12 into IR. And similarly, we have Z21 into Is minus Z22 into IR. Essentially, we have all voltages on one side, the corresponding impedances on other side in product with the corresponding currents being multiplied. So in a matrix form, we can rewrite this equation in this order. The reason why you have a minus sign here, because typically when Z parameters are defined, conventionally, the receiving end current notion has been defined as of this nature, different from the one that I am using over here. Since I am using receiving end current to be an output current, and for me this is not an input, so I have a negative sign. And as I mentioned, these parameters are impedances, so they are all in ohms. for a given two-port network, if I have to evaluate or figure out a way of evaluating these Z parameters, then it's very simple in the sense these Z parameters are essentially, so let's say if we have a case where the receiving end is open, in the sense receiving end is not feeding in any load. So in that sense, IR would be 0 and Z11 as per this equation would simply be Vs by Is for IR equal to 0, and similarly Z21 would be VR by Is for IR equal to 0. So if I have open circuit at the receiving end and I measure Vs, Is and VR using appropriate meters, I can physically evaluate these numbers Z11 and Z21. Similarly, Z12 and Z22 could be defined when receiving end is having some sort of electrical quantity, some source or load, and the sending end is open. Similar lines, if Z parameters can exist, which are impedances, on similar lines, Y parameters, which are admittances, can also exist. So in terms of admittance parameters or Y parameters, the relevant equation indicates relationship between the currents, sending and receiving end, in terms of sending and receiving end voltages. The current direction is reversed from the conventional nature, so that's why you would see a negative sign here. In typical textbooks, you may find a positive sign instead of a negative sign. And essentially, in matrix form, if the inverse of Z exists, if the inverse of this matrix exists, then the Y parameters are nothing but the inverse of Z parameters. Unit of admittance is sigma omega inverse or Siemens. So that's how the omega inverse sign comes in here. And the logic behind evaluating these Y parameters again remains the same, since we are relating currents to voltages. So instead of open circuiting the terminal ends, now what we would do, we would short circuit the sending end. So let's say if we short circuit the sending end, the corresponding voltage here would be 0. Sending and receiving end voltages are being measured with respect to some neutral or ground. So sending end voltage, once it is 0, the corresponding Y11, I1, Y21 would be ratios of Is and VR. This is not true for Y11, Y21. This is true for Y12 and Y22 where Vs is 0. Similar notion is also applicable for defining or evaluating Y11 and Y21. So given the physical network, I can use this sort of mathematical relationship, carry out certain experiments, open circuit and short circuit experiments, the way open circuit and short circuit tests are done for evaluating typical parameters of a given electrical element, be it transformer, generator. Same notion can be applied or used here for transmission lines. The third common property of parameters are ABCD parameters, in which the notion is a little bit different. On one hand, on one side, the quantities, they all refer to sending end, both sending end voltage and current, and the other side quantity, they pertain to all receiving end quantities, receiving end voltage and receiving end current. ABCD as the relevant parameters. So if one has to understand, oh, what are the units of A, B, C and D? So if Vs is equal to AVR plus BIR and Is is equal to CVR plus DIR as per the definition of ABCD parameters, then it's pretty obvious that Vs and VR are voltages, Is and IR are currents. So A and D are dimensionless quantities. Vs is voltage, IR is current, so B has to be impedance whose unit is going to be ohm. Is current, VR is voltage, so C is going to be admittance whose unit is going to be omega inverse or Siemens. So that's how this notion or logic comes in. This is ABCD parameters. They are common parameters in defining transmission line models, and again by carrying out different open circuit and short circuit tests at sending and receiving end, there's a logical way of evaluating these ABCD parameters. The last set is hybrid parameters or H parameters, where again it's a combination basically of ABCD and admittance admittance parameters. So on similar lines, H12 and H21, they are dimensionless, where H11 is impedance and H22 is admittance. It's a very common model representation, a parameter representation for modeling power electronics based circuits, power electronics based switches. By again carrying out different open circuit and short circuit tests, one can evaluate the corresponding H parameters also. So if one has to understand how these different parameters can be correlated or co-represented, Z parameters, we have seen that this is the relevant equation. So if one has to find the corresponding Y parameters, so basically if the inverse of Z exists and we carry out this mathematical operation, we would get Is in terms of Vs, Vr, we would get similar equation for Ir. So from where if we now plug in that Is, Ir is equal to Y11, Y12 minus Y21 minus Y22, Vs and Vr, these are all in vector or matrix form. So from there we can correlate the corresponding Y parameters in terms of relevant Zs. And remember, as I mentioned, the inverse of Z should exist. That means inverse of Z can only exist when this matrix here, which is the Z matrix, in terms of the matrix shown over here, it is its determinant is not 0. So if I find the corresponding determinant, the determinant here is Z11, Z22 minus plus Z21, Z12. That's the determinant of this corresponding Z matrix. If this matrix inverse has to exist, this determinant should not be 0. And that's the reason why you see corresponding similar term present in all the Y parameters in terms of Z parameters. For Y to exist, these terms or division should be defined. And additionally, if we now find Y11, Y22 product, we can use these expressions to correlate or find these relationships along the terms of Z parameters. Similarly, ABCD parameters can be represented in terms of Z parameters through a similar logic. I'm not going to spend much time on this because the discussion that we had for Y parameters represented in terms of Z parameters, the same logic is going to be applicable here for ABCD parameters. And on similar lines, the H parameters can also be defined in terms of Z parameters through corresponding mathematical analysis, provided the inverses or divisions do hold true. So what we have seen here so far in the last 3 slides are Y parameters, ABCD parameters, and H parameters are represented in terms of Z parameters. Other parameters can also be represented in other forms. So similar interchanges in terms of exchanges between these parameters is also possible depending on what is the need or the requirement needed. Few generic properties of these two-port networks. Usually two-port network, they have the property that they are linear and lumped. That means superposition theorem would hold true if we apply different open circuit test and short circuit test, or if we attach different types of voltage sources, again having a similar frequency, then superposition theorem will still hold true in the sense we analyze the circuit from one voltage source, get the results. We analyze the circuit for a different voltage source, analyze the results. And then eventually by adding these two voltage sources, we can still get the overall effect by adding the overall results. That's the beauty or property of linearity. And we can precisely point out specific locations in this two-port network against a fictitious representation where parameters are lumped and they are not distributed. Two-port networks often tend to be symmetric in the sense the effective impedance observed by this two-port network either at sending end or receiving end with the other port remaining open, it's going to be the same because we are considering it to be a passive network. The two-port networks often are also reciprocal. That means the cross impedances or cross admittances of currents and voltages in terms of, if we talk about cross impedance, then ratio of sending end voltage with respect to receiving end current under certain condition, or in terms of cross admittance, ratio of receiving end current with respect to sending end voltage, these numbers remain the same irrespective of what the port positions are. That means the ratio of Vs by Ir and ratio of Vr and Is, they would remain the same, they would be equal to each other irrespective of the port position. That's the property of reciprocality. And these network parameters, they are time invariant. So basically the performance remains the same no matter if we analyze the circuit now or at time t is equal to infinity. The overall steady state behavior is not going to change unless the inputs themselves don't vary in time. In the sense, in phasor domain, for fixed inputs, you would get fixed set of outputs. The parameter or behavior won't change because the two-port networks are basically passive elements. So for conditions of symmetry, if we want to understand, then in terms of Z parameters, this is our equation, the model, with sending end excited by a voltage V and receiving end open. That means there is no load under the receiving end, so IR is 0. The associated sending end impedance is Z11, which is V by IS. And again, if we do the same thing on the receiving end that means we excite the receiving end by V and open the sending end sending end port. Then we have Z22. For symmetricity, V by IS should be equal to V by minus II. That's the property of symmetricity. So essentially, for in terms of Z parameters, Z11 and Z22, if they are equal for a two-port network, the two-port network is called as symmetric. Other relationships in terms of Y parameters, ABCD and H11, H22, they can also be defined using the relation that we talked about. For reciprocity property, the ratio of the cross impedances are matched. So basically, if the network is reciprocal, the values of Y12 and Y21, they would be equal, and on similar lines, the corresponding relationship in terms of other parameters, Z, A, B, C, D, and H, they can be defined or evaluated based on the discussion that we had earlier. So that's all for today's discussion. In the next lecture, we will take up our basics of two-port network and apply it for understanding short line model. Thank you.